We're now on 7.4, formal charges and resonance. In this section, we're going to compute formal charges for atoms in any Lewis structure, use formal charges to identify the most reasonable Lewis structure for a given molecule, and explain the concept of resonance and draw Lewis structures representing resonance forms for a given molecule. So just as a little introduction, sometimes it may seem as though there are more than one possible Lewis structure for a molecule. So when we were doing the Lewis structure where the carbon had to double bond with one or two of oxygens, there's an example. And there are times where there is more than one possible Lewis structure. Other times we need to look a little closer to figure out what the correct structure actually is. So we do that by using formal charge. No, it's not a charge in a suit and tie. The formal charge of an atom in a molecule is the hypothetical charge it would have if we could redistribute the electrons in the bonds evenly between the atoms. It is not a real thing. The atoms do not have these charges. It is all hypothetical. It does not indicate the presence of actual charges. The way that you calculate the formal charge of an atom is you take the number of valence shell electrons minus the number of lone pair electrons minus 1/2 the number of bonding electrons. And when you add up all the formal charges of the atoms in a molecule, it should equal the charge of the whole molecule or ion. So if you have just a regular molecule, it needs to equal 0. But if you have a charged ion, for instance, -1, it should overall equal -1. If the ion is overall +2, your overall formal charge is +2. Again, remember, formal charge does not indicate the presence of an actual charge on the atoms themselves. So let's look at an example. And I purposely don't have any information here from the book because they kind of change how they calculated the formal charges of everything. It ends up being the same answer and everything, but I want to stick with our original definition on how to calculate formal charge. So we want to assign our formal charges to each atom in the inner halogen ion ICl4. So the first thing that we need to do is we need to draw the Lewis structure. Step 1 is to draw our Lewis structure. So let's get our valence electrons. Iodine has 7, and chlorine also has 7, and we have 4 of them. And we have a -1 charge, so we need to add an electron on. So now we have a total of 36 electrons. So we're going to have iodine in the center, chlorine around it. Start with all of our single bonds. 8. Now we have 28 electrons. So let's go ahead and fill in our chlorines. 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24. We have 4 electrons left over, which means 2 sets of lone pairs for the iodine. Now we've used up all our electrons, so now we can go ahead and do our formal charges. So iodine, formal charge, it has 7 valence shell electrons minus the number of lone pairs, and it has lone pair electrons. So there's 2 sets of lone pairs, which means a total of 4 electrons, minus 1/2 times the number of bonding electrons. So it has 4 single bonds, which means there's 8 bonding electrons. So 1/2 times 8. We have 7 minus 4 gives us a formal charge of -1. Oh, that reminds me. I got to put the negative around our molecule. So each chlorine is going to have the same formal charge, 7 valence electrons, minus 6 lone pairs electrons, minus 1/2 times 2 bonding electrons equals 7 minus 6 minus 1. That equals 0. So if we were to add up -1 plus 4 zeros, we get -1, and that's what is our overall charge. So formal charge on iodine is 0, or -1. Formal charge on each of the chlorines is 0. Next up, we're going to do formal charges for BrCl3. So starting with getting our structure, bromine, 7 valence electrons, times 1, chlorine, 7 valence electrons, times 3 is 21, so we have 28 electrons. Put bromine in the center, 3 chlorines around it, single bonds, -6. We have 22 electrons. We're going to fill in the chlorines next. 2, 4, 6, 8, 10, 12, 14, 18. 4 left over. That means bromine now has 2 lone pairs of electrons on it. Formal charge time. The bromine, 7 valence electrons, minus 4 lone pair electrons, minus 1/2 times 6 bonding electrons, gives us 7 minus 4 minus 3, a formal charge of 0. Next, each chlorine, formal charge is equal to 7 valence electrons, minus 6 lone pair electrons, minus 1/2 times 2 bonding electrons. That's 7 minus 6 minus 1 equals 0. So everything has a formal charge of 0, which makes sense. You add all those up and you get overall 0 because this molecule is a neutral molecule. Now we can use formal charge to predict molecular structure. So the way we do that is there's some guidelines that we're going to use. And the arrangement of atoms, just for your information, the way we arrange the atoms in a molecule is how we get the molecular structure. That's what we call the molecular structure. So we have 4 rules to determine which possible structure is correct when you have more than one that seems like it can work. The number 1 guideline is that a molecular structure in which all formal charges are 0 is preferable in which non-zero formal charges exist. So if you have 3 structures to choose from, that you, for instance, that you see on the bottom for CO2, and you calculate the formal charge on each atom, and you notice that on the far left with carbon in the center, each atom has a formal charge of 0, whereas the other 2 have formal charges on them. So it's preferable then that all the atoms have a formal charge of 0, which means that far left carbon in the center with 2 double bonds to each oxygen is the correct structure. The next guideline is that if there has to be some non-zero formal charges, the arrangement with the smallest non-zero formal charges is preferable. So, for example, the thiocyanate ion, there is going to be some -1 somewhere, and it's going to have to be this guy on the far left, because this structure here with the carbon in the center and nitrogen and sulfur on either side ends up with only 1 atom with a formal charge. So and it's the smallest one as well. It's only 1 atom with a formal charge, and it's only -1. The next guideline, Lewis structures are preferable when adjacent formal charges are 0 or the opposite sign. And the 4th one is when we must choose among several structures with similar distributions of formal charges, the structure with the negative formal charges on the more electronegative atoms is preferable. So let's look at an example. Nitrous oxide, or N2O, is commonly known as laughing gas. This is used as an anesthetic in minor surgeries, like getting your wisdom teeth pulled. And we want to figure out the likely structure for nitrous oxide. So we're given 2 potential structures, and what we need to do is figure out the formal charges on the atoms and then go from seeing which one best satisfies the criteria that we've been given about finding the most stable structure with formal charge. So let's start by looking at the left structure that goes nitrogen, nitrogen, oxygen. The far left nitrogen's formal charge is going to be equal to valence electrons, 5, minus the number of lone pair electrons, 4, minus 1/2 times the number of bonding pair electrons, or bonding electrons, and it has 4. So that means we have 5 minus 4 minus 2 has a formal charge of -1. Our center nitrogen has a formal charge of 5 minus 0. It doesn't have any lone pair electrons on it, minus 1/2 times 8. So that is equal to 5 minus 0 minus 4, positive 1. And lastly, the oxygen on this guy is equal to 6 valence electrons minus 4 lone pair electrons minus 1/2 times 4 bonding pair electrons. So that's 6 minus 4 minus 2. That is equal to 0. So now we know we have a -1, a +1, and a 0. On our other molecule, whoops, the far left nitrogen here is going to have a formal charge of 5 minus 4 minus 1/2 times 4, just like the last one did. So that's again -1. So this guy has a formal charge of -1. The center oxygen here is going to be 6 minus 0 minus 1/2 times 8. So that is equal to 6 minus 0 minus 4. And that gives us a positive 2. We can already kind of tell this is probably not going to be the right molecule because now we have a higher formal charge with that +2. And just for completion, this other nitrogen on the end, it's identical to the other one, so that's also a -1. So looking at this now, we can see that our left molecule is going to best satisfy the criteria to have the most stable distribution of formal charges. So the last thing to talk about in this section is resonance. So sometimes there can be multiple structures with the atoms in the same positions, but the electrons in the double bond are in different places. So for instance, NO2, be a subscript 2. It seems as though there should be a double bond between nitrogen and oxygen, but which one? So if you look on the bottom of the screen, that shows you this nitrogen in between oxygen, and this is NO2 minus. Sorry for that typo. So, if I were to ask the class and have everybody draw me the structure of NO2 minus, I'd probably get a pretty even distribution of the double bond being on the right versus being on the left. So experiments for this molecule have shown that the bonds actually have the same strength and length. A single Lewis structure then is not possible. So these bonds end up actually being identical. And one of these Lewis structures is not correct. Neither one is correct. So the concept of resonance is used when you have 2 or more Lewis structures with the same arrangement of atoms that can be written for a molecule or ion. So the actual electron distribution is an average of what the Lewis structures show. So each individual structure is called a resonance form, and the actual structure is a resonance hybrid. So we can rewrite these guys by putting a arrow going back and forth to show that these are resonance forms of each other. When the resonance hybrid looks more like this, okay, where you have this equal distribution of electrons, and then it kind of goes, and each oxygen is kind of sharing that electron density. So again, neither resonance form describes the electronic structure. It's always an average of your resonance forms. George Wieland actually used a historical analogy of how rhinoceroses were described as hybrids of dragons and unicorns. They have some properties in common with both dragons and unicorns, but it isn't a dragon, or is it a unicorn? I wish it was a unicorn. And then another example of a compound with some resonance forms is the carbonate anion. You can see each of these oxygens has the same chance of forming the double bond with carbon. When in reality, it's something like this, where you have the shared electron density across all three bonds.